Let's start from current slide. All right. Now, just a couple of things. I won't belabor this too much, but I did see signs scattered around the building. On Friday, there's a presentation of The Taming of the Shrew, which is a William Shakespeare play. I think it's being put on by the UAB Theater group, and it's going to be on the Birmingham East Campus at Gaston Autos. Goodness, how do you say his name? I can't think of it. It starts with a G. Yeah. It's the auditorium there in the big building on Birmingham East Campus. Flying the coop right now. And anyway, it's 10 o'clock in the morning on Friday. I'm guessing probably most of you are not all that interested. Supposedly, they are reversing the roles. The original Shakespeare's version of Taming of the Shrew had a very strong-minded, strong-willed woman, and the guy was trying to tame her. That was where the name came from. And evidently USB has decided to... It's a comedy, by the way. It's a comedy. It's not a tragedy or a melodrama or something like that. It's supposed to be a comedy. And so UAB has decided to do it with the male being very difficult and the woman trying to tame him. But if you're interested, it's there on Birmingham East Campus, Friday at 10. Okay. Let's just go from there. Well, remind me before we take our break, whenever that is, to find out if anyone is heading east and could give me a ride, because I don't have a ride home tonight. My wife can come get me, but if anyone's heading east, I can go as far as you're going, and then she won't have as far to come and get me. But we'll talk about that at break. And let's go on from there, because I don't have a car right now. Okay. First thing I think that we are about to do is talk about the lab. I take it you didn't get to finish last time, right? Okay. So some of you may have... Oh, I knew there was one more thing. The other reason I was sort of running late, I wanted to make sure that I checked with the bookstore before I came to class, and I did. He said the book should be in either later this afternoon or tomorrow. Okay? He said, get a count again. How many of you did need a book? When I counted before, it was fewer than 10, but how many of you do need a book? Okay, 1. Now, did you get one for the first course? Okay. Did they pick one? Yeah. Okay, same book. Okay, you got it. Okay. 1, 2, 3. That's all there. 4, 5, 6, 7. Is that all? He ordered 10. So if that's all you need, they should be here and able to handle that, hopefully by tomorrow. Okay, so I wanted to get that clear. And he just screwed up. I mean, he tried to say this, that, and the other thing, and finally I said, look, this is, oh, yeah, we screwed up. So finally it admitted it, but yeah. And they got them ordered supposedly second day delivery, but evidently they didn't acknowledge the order until yesterday. So I don't know. It's supposed to have gone out last week, second day, but I don't know. All right. I just don't know what to believe of them. Now, okay. So, any questions on, now for those of you who have the lab and you haven't even started it, you'll need to get with someone, and everyone still has their lab, so you can get with them, get the data from them. The lab's in 3 parts. The first part is drawing circles and taking down data. The data you recorded on the table next to the last page, page 23, top of the page, circles and ratios. And all of you got the data for that, except the people who weren't there. And you've done your calculations. Were there any questions on that? I think y'all did fairly reasonably well on that, it seemed like, just looking at the numbers I was seeing. Okay? Then the second part was playing with blocks, area and volume ratios. Okay? I did see some errors popping up there. I hope I caught them all. Those data you should have recorded at the bottom of page 23, area and volume ratios. Does anyone have any questions or doubts or questions about those, problems with those? You're okay with that? Okay. If you have any questions, see, yeah.
We never got there. The group that was, I guess, the farthest in group, that was, I think was doing medium.
Okay, yeah, that's the third part. So I'm not going to, the blocks.
Yeah.
Everybody got the blocks with that. Okay. All right, now we're ready for the third part. The third part was the directions. Okay, directions for the first part. Part A was on page 15. Part B was the top of page 16. And part C, that's the one we're going to hit now, was the bottom of page 16 and on to 17 and 18. And that was the part that I didn't discover there's a big problem on until right at the end. And I think someone misread the scale or something pretty badly.
Yeah.
There were some late adjustments there. Did everyone get those, or did they answer all the? They did not.
We never got the, I think it was for the medium. It was.
Yeah. I can't say what, and these data on page 24.
Medium or large? Medium. Okay.
Yeah. It's on page 24, and I can't tell you 1, 2, and 3 because every team put theirs in a different column, so I can't say, but there was a small container, a medium container, and a large container. Okay? If my memory's right, the medium container had way too small of a number on it. Okay, and that was mass of the water. Was that what was the number that was off?
Well, it ended up being all of it was just weird.
Okay.
They're all
okay.
Accurate.
Do we need to go back and redo
we
the whole?
We had everything right until we got to the mass container and water, because apparently we had to pull our all the way up to water. That's when things started going south, was at number 6.
Okay, well, I thought somebody went back and refilled.
You helped us take more measurements and we got it right.
Okay, what number did you get to correct that then?
For 6 I have.
What do you have?
For 6 I had 187 grams.
Okay, tell me what you had on the small and large.
Small is 119 and large is 67.
Is what?
Large was 67 grams.
67 grams?
No.
No. Okay, that I think was 567 because I think the thing went all the way around and.
I did too. I got 491.
Is that right?
I got 491.
491. Okay. I don't know where that came. 491.
Small, I got 119.
119, and the medium was what?
And 187.
Okay.
187. Those sound like reasonable type numbers then.
I had 113 for the medium.
113?
For line 6 or 7?
Yeah, 113 was our first number, and that ended up being wrong. So it's 187.
Okay. Let's start with number 5, massive container. Well, those are all pretty small, and everybody got those right. So number 6, massive container and water. Consensus, small. What you got there?
119.
119. Is that across the board pretty much?
Yes.
119. Okay, number 6 for the medium.
187.
187. Now that sounds fairly reasonable.
That was everybody had.
Just tell me, what was your calculated volume for the medium?
179.
Okay, that sounds very reasonable. Okay? All right. What was your measured volume of the medium? Number 8.
84. 84
I don't
Okay, that again, that's closer to what you had for mass, right? Before you made the changes.
Closer to what we had to massive.
Number 6 for medium.
Well, number 6 we had 113 wrote down.
Okay. All right. Okay, so, well, 84, it doesn't sound like a reasonable measured volume either. Do we need to go back and measure that? Did anyone have a measured volume for the medium that's number 8, different from 86 or something?
I had 48 down when I recorded the room.
Okay.
48?
Okay, that is low even for the small container.
Yeah.
84 is too low.
Yes.
Yeah, what was the small container?
Small container is 119.
Yeah, so you see that.
So we should have a higher than small.
It should, yeah.
Higher than 119, lower than.
So we obviously need to redo the measured volume of water
Okay,
for ours.
all right. Okay, well then, when we go to lab, that'll be the first thing we do. The medium container, we'll do the measured volume. And you think everything else is okay then?
The mass of water for number 7, for medium, is 105?
No.
176.
176?
Okay.
Well, wait, yeah. If you got massive container and massive container of water, if you got 5 and 6, just subtract them, you should have 7. Right?
What'd you get for 5?
10.1.
Yeah, I got that.
That shouldn't be very far off from any of them. They should be.
76 right now, 7.
Yeah, that's what he just said.
What you got for mass of water?
Is there any other questions? So when we go to the lab to do today's lab, which is going to be very quick, you'll be done in much less time than it took the other one. It will take me longer to set up because I was in the bookstore or on the phone or with my, it was just crazy. All thing I didn't get to set up for the lab, but it won't take that long. Yeah.
I have a question for you. Since we're not going to be getting the adjustments right until the end of class, basically.
Right.
Can we turn this back in Thursday?
Oh, you have 1 week from the time we complete the lab. We'll complete the lab today, so you have until next Tuesday.
Gotcha.
You can turn it in Thursday if you want to.
Is that all
Okay.
we do? We have 1 week to the time we leave the class and finish?
Well, 1 week from the time you finish the lab, you have that. A lot of times you're going to finish the lab in the lab and you'll turn it in. That's up to you, but you always have a week to do it.
Okay.
And, yeah. Okay. So, we'll be okay once we get the measured volume of the medium container.
Right.
So we'll do that, and it won't take long. Yes.
Can we make sure? Okay.
Obviously, we'll have to redo 9 and 10 too, because the number.
Yeah. You can't do the calculations until you get the numbers. That's why I give you a week after that.
Can we make sure we're in consensus for small and large too? Just check what we're doing, small and large, see if we're all have the same numbers.
Yeah, you can do that in lab, can't you?
Okay, in lab.
Yeah. Okay. All right. Now, okay, that's the measurements. This lab has more extra measured things than just about any of the other labs you're going to do. Now, once you get the data, like you say, for 9 and 10, well, actually, all the data, basically 7, 8, those kinds of data, then you'll be doing the plot. But you can't do your plots until you get the correct data. Okay? So hang on to that until then. Huh?
They'll have to do 6 through 10, correct?
Right. Okay. So you can't do that. So questions over here on page 18. At the top of the page it says number 6, make a graph, draw a straight line, calculate the slope. You can't do any of that until you get
the graph wrong.
you get the correct data. All right. Now, by the way, most of these labs that came out of the lab book, these are the ones that say experiment across at the top and that kind of stuff. Today's lab will not say this. This is one I came up with. Okay? But all these, you'll have somewhere in the lab, and on this one, it's on page 18, number 7, was the purpose of this lab accomplished? Why or why not? Your answer, blah, blah, blah. Give me a sentence or two, that's all. I don't want, if you want to write a paragraph, you can, but all I need is a sentence or two. I do need a little more than yes or no, but just a sentence or two will be fine. But this lab, like I say, has some questions other labs will not have. And that's under results. And did anyone get started on these? Okay? These are things either you get from the reading or from your text or basically what we talked about. If you have any questions on those, bring those to me too and we can discuss those. Did anyone get going on them and wasn't sure what to go with? Okay? So do those. Don't forget to do, that's page 19 and the top of page 20. And then this lab again has something most other labs don't. In fact, none of them that I can recall. Problems. Okay? And this problem is based on an aluminum block, 1 meter by 2 meters by 3 meters. A big old aluminum block. And it tells how many kilograms it is. Okay? And then it has a bunch of questions about that block. Okay? Some of it is changing those dimensions to centimeters, which then would be calculating the area in square centimeters and the volume in cubic centimeters. This is over on page 21. And then converting the mass that you saw on page 20 from kilograms to grams. So if you have any questions about any of that, please ask. Don't flail around in the dark and give me garbage. I'd rather you learn something from it, so ask questions if you have it. Okay? And then the rest of it is your data. So if you have any questions on any of the labs, please ask me, and I'll try to explain it for everybody. Okay? Because the odds are if you have a question, I'm guessing just about everybody else probably would have had the same question. Maybe you're a little ahead of them and they hadn't got to ask it, but they would have. All right. Any questions? Can we do everything? Are there any questions on that lab you want cleared up now before we go, in the lab later and take that last measurement? You think everything's fairly clear except that last measurement? Is that right? Okay. All right. If not, please ask. Okay, in order to be ready for the next lab, let's continue here. We had done speed, so we've done this slide, but we hadn't done example 2.2 on page 28. Were there any questions before we start there? Okay. Example 2.2 says a bicycle has an average speed. What symbol have we been using for average speed? Anyone have a clue? V bar. Second. Yeah, V with a bar on top. That's it exactly. It has an average speed of 8.00 kilometers per hour. 8.00 kilometers per hour. Now, what's those two zeros doing there? They just throw them in.
It's accurate. It's accurate.
This is a very precise measurement. Not to the nearest kilometer, not to the nearest half a kilometer, not to the nearest tenth of a kilometer per hour, but to the nearest hundredth of a kilometer per hour. It's right on there at 8.00 kilometers per hour. In other words, 3 significant digits. That's all you have to really know, but that's what that means. Very, very precise measurement. How far will it travel in 10 seconds? So what are we looking for? How far? Distance. This is the unknown. Okay? And it tells you in 10 seconds, what's that a measure of? Time, or time interval, and that would be 10.0 seconds. You have a very precise stopwatch. Okay? Gives you to the nearest tenth of a second. Yeah, right. Okay? Now, what would be your approach to that problem?
We would have to change kilometers to...
Exactly.
Find kilometers a second.
Probably changing kilometers more than likely to meters. Okay? But more obvious here is changing hours to seconds. Okay? But when you do that, you're going to have such a small number of kilometers to travel in a second that you probably are going to want to change the kilometers to meters at the same time. And I think they give their answer in meters. So let's start with our 8.00 kilometers per hour, and let's convert that to meters per second. No, let's do kilometers per second. Let's go on to meters per second. I'm going to put 3 sets of conversions here. You may not use them all, but the reason I put 3 is to go hours to minutes, minutes to second, and kilometers to meters. Okay? You don't have to do them all at once, but I thought since I don't have much room, I'll go into them. Why did I put 2 blanks here?
One for the numbers and one for the...
One for the numbers, one for the units. Which you put in place first? Units. Always put the units in their place. Now which, yes. Oh, which you want to convert first? Kilometers to meters, hours to minutes, or hours to seconds, or minutes to seconds? You tell me. Hours to minutes, okay? Where will I put what unit then?
We'll put hours at the bottom.
Really? Okay, hours on the bottom, minutes on top. When you multiply, we'll mark Chelsea here, okay? All right. If you were to do this, what are you going to wind up with? Kilometer, meters, minutes per hour squared. Is that really what you want? No. Okay. So I think we may have it backwards. Make another guess. Say again? Hours on top and minutes in the bottom. So you can divide out your hours and have kilometers per minute. Yes, that will make more sense. Now that we got the units in their place, that's why you put the units in their place first. Now you match the numbers with the units. How many hours in a minute or how many minutes in an hour? Second?
1/60.
Okay, 60 minutes is 1 hour. Got it. Next, what you want to do? Minutes to seconds. So which will you put where? Minutes on top and seconds on the bottom. Okay? And what? Yeah, the minutes will cancel out. And what numbers go with the units? Say again? 1 minute is 60 seconds. Very good. And now, since you've gotten those to be, so you see what's going to happen here. If you left it with 8 kilometers, divide that by 3,600, you're going to have such a tiny little number. Who wants to measure that in that smaller number? So let's go on and get to a bigger number with a smaller unit. So let's go from kilometers to meters. So let's do that last one. Now what will that be? What will you put where?
Meters on top.
Meters on top, kilometers on the bottom. That will cancel your kilometers out. What numbers do I put to match up meters and kilometers?
1,000.
1,000 meters is 1 kilometer. All right. Now you multiply numerators. Oh, and by the way, yeah, you're left with everything's canceled out except meters per second. That's what we wanted. Okay? So you multiply numerators, divide by the denominators. Now you can go on and multiply the denominators first, then divide. It doesn't matter. So that would be 8,000 divided by 3,600. Right? Anyone got a calculator?
$8,000 divided by 3,600.
Right.
2.23.
2.23. Okay. And that.
2.
Okay. Well, then make it 2, because the next 2 doesn't round up.
I wasn't rounding off.
Okay. So that would be meters per second. That is now the average velocity. Okay. 2.22 meters per second. Why did we put 3 2s down there? Because we have 3 significant digits everywhere. These are significant. They're exact. 60.00000000 minutes in an hour, and same thing with seconds in a minute. You can put those as precise as you want to, and exactly 1,000 meters per kilometer, 0.00, as many as you want there. So those are exact conversions. Not all of your conversions are exact. Those are. Okay? So that gives you that. So now we get back to our question. You've got the units straightened out. How do we find the distance?
Multiply 2.2 meters per second by 10.
Okay. What I hear you saying distance is average velocity times time, which will, in this case, we'll use the 2.22 meters per second multiplied by 10.0 seconds. Oops, I left off my unit. The seconds cancel out. That gives you meters, a very good unit to measure distance in. So what would that be? 10 times 2.22.
22.2.
22.2. That it? Meters. Okay. Don't ever leave off your units. $6 billion errors, remember? Okay. All right. And that's what they got, 22.2 meters, approximately. Okay. They have a couple of concepts applied here, speeds, style speeds. I found that one a little lame, but if that's of interest to you, look at it. How fast is a stream? That's something that's a lot more practical in my mind, or useful, and it gives you a couple of ways to go about estimating that. But even then, just in general, stream of moving body of water, how could you measure the speed of the stream? Would timing how long it takes to float a floating leaf to move a measured distance help? Sounds like it to me. Okay. What kind of relationship, if any, would you predict for the speed of the stream and a recent rainfall? Yeah, it would go faster. Okay. Would you predict the direct relationship? I think so. Make some measurements of stream speeds and compare, blah, blah, blah. That's only if you want to. But here's another thing they didn't mention. You drop the leaf in the middle of the spring, you're probably going to have a much more accurate. Along the edges, you got more friction, and usually things don't move as fast there. So where you put the leaf also would make a difference. But they weren't talking about that. All right, any other questions on the concept of speed? Okay. And by the way, there was the formula we used. Speed is equal to distance. Yes?
I did have a question. I just wrote these down for me to help remember them. What did the V with the dot over it, over the top of it mean?
What's that again now?
The V with the dot over the top of it, what did that one mean? Because the V
Where
over
did
the
you
line is the average.
Average. Where did you find that with a dot?
Or whatever the other one we used was. I might have wrote it down here. We used another one, another V.
Okay. I may have written, I don't know, something like this, V with an arrow over it. Would that have been it? Okay. Well, that was Ashland coming in. No, I'm sorry, that's something else. Okay. All right. What that means, that is your vector velocity, and that's average speed. We use V for both of them. When you talk about averages, you usually don't give directions with averages. It's just how fast something's going. But this is an actual speed in a given direction. That's velocity, a vector quantity. So if that's what it was, that's the only other thing I could think I'd put over a V. When you said the dots, Isaac Newton used dots to represent derivatives. I thought, surely I didn't say anything about that in this class. Some of you may know about derivatives, but that's not the purpose of the course. So there's the formula we use, distance equals speed over time, but y'all changed that around to be distance equals speed times time, and that was the formula you used. Good deal. Okay. And I think we already did this with average speeds, didn't we? I'm pretty sure we did. Yeah, there's the formula. Now this may have looked like a dot, but that's just a very short bar. Okay, so, all right. I think where we began today then is on with velocity. That's what I was just getting. That's why I was sort of surprised I did anything with it, because we hadn't actually gotten to it yet.
I think you were just explaining the whole vector thing.
Yeah, could have been. Okay. So, what is velocity? It describes speed, how fast something is going, with a direction. Where is it going? What direction is it heading? And I think I used examples before, like traveling from home to here. my average speed would have been maybe 20 miles per hour. 70 miles, well, no, more like 50 miles an hour, averaging on the road and on the neighborhoods and stuff like that. But, no, it's probably closer to 60. But the velocity would have been 60 miles per hour to the southwest, because from home, south side of Birmingham to Bessemer, I'm heading sort of on the southwest. So speed doesn't tell you anything about direction. Velocity tells you about speed, how fast are you going, also including the direction. Okay? Now, graphical representations of vectors, the length of the vector is considered to be its magnitude. That's just another name for length. The arrowheads indicate directions, and we'll be using these throughout the course, not to huge extent, but we will be using them. They will indicate direction. So if you see something with an arrow, that is a vector, not just a scalar number. Okay? I don't think we had this slide, did we? Okay. Here is a car traveling 30 kilometers per hour to the east. Okay? Here's a car traveling 60 kilometers per hour to the east. Notice the length of the vector is basically twice as long, but the direction is identically the same. So, different speeds, same direction. Okay? However, this one is the same length as this one, 60 kilometers per hour, but it's going to the northwest. So, none of these are equal vectors. Even though these have equal lengths, the speeds are the same. The vectors, the velocities are definitely not the same, because velocity includes direction with the magnitude. Okay? So these are all different velocities. These two would be the same speeds, but all these are different velocities. Okay. Kind of makes sense? And that's all they do on velocity. Really pretty weak on velocity here. Now let's move to acceleration. Let's see. Give me a flashback here. What is speed or velocity? How do we define it? Time, rate of change of distance or displacement. Exactly. You get a quantity, work with it some, get all the information from it, and then say, well, what happens if you take the time rate of change of that? Then you get a new quantity. Well, the time rate of acceleration is the rate at which the motion or velocity is changing over time. Okay? The rate at which the motion or velocity is changing over time. So, if I'm going along at the same speed, is my velocity changing? No. So what is my acceleration? Zero. Okay? If I'm going along, but then the speed increases, the velocity is increasing, the acceleration would then be positive. Okay? Not zero any longer. Or, if I started backing up slowly and then was backing up faster over time, I just stopped myself before I ran into Kedrick. Okay? He is thankful. Okay? What is happening there? The velocity is negative because I was backing up, but increasing in that, so the acceleration is negative. Okay? A large negative number. Because the final velocity was much less than the initial velocity. It's kind of backward, wacko when you get the signs in there. But so, okay, how about this one? I'm going with constant speed, but I'm changing direction. Am I accelerating? Yes, I am, because velocity is changing. Velocity is not just speed, it's speed with the direction. If velocity changes, you've got to be accelerating. Okay? Have you ever wondered why the banks at Talladega or every other racetrack are raised like that? The turns. The flats, the straightaways are flat, right? But the turns are banked. Why?
You go faster at an incline.
What's that?
You go around the curve faster instead of incline.
You better, because the
velocity is going to cause
you have to be accelerating when you go around the curve. Even if your speed's not changing, you have to be accelerating because you're changing your velocity. So something has to be pushing you back. If you're counting on just the rubber on the road to give you that, you're skidding into the stands by then or somewhere, where you don't want to be. So they bank it. So, and not just there. Expressways, curves are banked. I don't know if any of you come in from the east on I-20, where it merges into 59, there near the airport. Okay? Okay? If you'll notice there, they dropped the speed limit way down. And the reason is it's a very tight turn, and they didn't have enough room to get a good enough bank on it. If you try to make that bend there at the same speed you were back there, it's sort of fortuitous that right across the fence there, does anyone know what was there? A cemetery. Okay, so.
Isn't that what they call a dead man's curve?
Yes, I believe that may be what they call it. Okay. You don't want to go there, so slow down. Pay attention to that, because your tires cannot provide enough change of acceleration to get you going there. Okay? So the rate at which motion or velocity changes over time, the speed can change, the direction can change, or both speed and direction can change, and a velocity or an acceleration can be negative. I just sort of illustrated one. Okay? Here's another negative acceleration. My final speed was very small. Initial speed was very large. Initial minus final. Final minus initial is going to be a negative number because that number is bigger than this one was. So acceleration can be negative. Okay? Speed is not negative. Even if you're going backwards, you say, I have such speed. Velocity can be negative. Acceleration can be negative. They are vector quantities. The direction is partly expressed in whether it's positive or negative. All right, so here we have a car going at 30 miles per hour here, but 60 miles per hour there. Is it accelerating? Yes, you better believe it is. Okay? If it's going from 60 miles per hour here to 30 miles per hour here, is it accelerating?
No.
A negative acceleration. It is acceleration, but it's a negative number. Sometimes we call that decelerating.
Why do we call it deceleration?
It's just sloppy word usage, okay? It really should be a negative acceleration. If here it's at 30 miles per hour and it's still going 30 miles per hour, is velocity changing? Is it accelerating?
Yes.
Yes, it is, because the direction is changing, and acceleration is change of velocity for change of time. Time rate of change of motion or velocity, not time rate of change of speed. If it was time rate of change of speed, that'd be a zero acceleration. It's not. That you have to be pushing inward there. Here you started at 30 miles per hour, you went around the curve and came out at 60 miles per hour. Probably not the smartest move ever, but are you accelerating? Yeah, you better believe it. You're accelerating by being on the curve, and you're accelerating by changing your speed. So both of those could change. Okay? Does that make sense? All right. Now, there's something we call uniform acceleration. What's that? That means y'all are wearing uniforms. No, that's not okay. What it means here is that you have constant straight line acceleration. In other words, your acceleration isn't changing. The velocity is changing, but the acceleration is not. Constant acceleration, straight line acceleration. What are some things that might move at constant acceleration? Say again? Dropping something. When you're dropping something, it's picking up speed at a constant rate. Say again? Okay, a treadmill may be. You aren't going to do it too long, constant acceleration, because you can't go that fast. Okay, it will very rapidly get past what velocity you can endure. Okay? The average velocity is simply related to the initial and final velocities in this case. Okay? If you have constant acceleration, uniform acceleration, it's the same acceleration, not the same velocity, the same acceleration, Another way you can do it, rather than change of speed over change of velocity over change of time, that's one formula. Another one would be just take your initial velocity, your final velocity, average the two, and that's going to be your average velocity. So you have two ways to calculate average velocity if you are traveling at a uniform acceleration, constant acceleration. You can either do change of velocity over change of time, that certainly will give it to you, or initial velocity, add it to final velocity, average, divided by 2. That also gives you average velocity. Okay? Two ways to get it. Any questions on that? All right. And here's the formula. So average velocity before was change of position over change of time, change of distance over change of time. Okay? That gave you average velocity. Here's the other way. If you have constant acceleration, final velocity plus initial velocity divided by 2. We will use this one in lab today. Yes, sir.
So you said V bar is average acceleration?
No, this is average speed. Sorry.
Okay.
Average velocity, average speed is this.
Okay.
It's constant acceleration. Acceleration is not changing, but the velocity, of course, is. If it's accelerating, the velocity is changing. Got to be. We will use that one in the lab today. We will manipulate it some, move it around some, but we will use it. All right, everybody got it? All right. Now, we move to the next concept here. So this is actually what we just did covers today's lab. We're moving now to the next part. And by the way, I wasn't turning the pages frequently enough. If you haven't noticed it from lab, this author likes graphs. Just about every lab you do that I take out of the lab manual, not everyone, but most of them have graphs associated with it. Those that I come up with most of the time don't, but you know, the ones they provide do. And on page 28, this is sort of flashing back here, there is a graph of, not all of you have books, so it's going to be hard to read from back there, but what you have here is distance on the vertical scale, time on the horizontal scale. So guess what your slope measures? What is slope? Rise over run. Rise is change of distance. Over run is change of time. Distance over time is velocity or speed. So that's exactly what your slope of your line is, especially if it's straight line motion like that. Now, if your distance is changing evenly with time like that, what we know then is you have a constant velocity because the slope is always the same. Okay? Now, flip one page. One piece of paper is 2 pages. Okay? Here we have speed versus time, not displacement versus time. Now, what does that tell you? The speed is always the same. After 1 hour, after 2 hours, after 3 hours, the speed is the same. That's a constant speed. What would be its acceleration? Constant speed is zero acceleration. You're absolutely right. Now this graph shows changing speed over changing time. That means you are accelerating. Again, rise over run, change of velocity over change of time. Now I don't like they're still calling them y here. I would call that delta v over delta t. That's acceleration. Now that would be constant acceleration. What's the other name we use for it? Uniform acceleration. Exactly. Okay. Now, that brings us up to okay. They give a couple of examples in the book, and let's do those first before we get to forces. Let's see if there's a better. Okay, right here, this will do, I guess. Acceleration due to a change in speed only can be calculated as following. Consider a car that is moving with a constant straight line velocity of 60 kilometers per hour. Constant straight line velocity at 60, was it kilometers per hour? Yeah, kilometers per hour. Okay? He's going along there, constant. When the driver accelerates and goes from 60 to 80 kilometers per hour. Okay? Suppose it takes 4 seconds for that to happen. Okay? For that change to occur. The change in velocity is therefore, what's the change of velocity? Okay, acceleration is change of velocity. Remember, delta is difference in or change of velocity over a change of time. Okay, so what was our change of velocity here? 20 kilometers per hour, not just a number, but a unit as well. And what's your change of time? 4 seconds. Now you could go back and change everything to that, but this is a legitimate acceleration. That would be what? 20 divided by 4? 5 kilometers per hour per second. That's the change of acceleration. That is an acceleration. Okay? Now, y'all are probably a lot more used to talking in terms of miles per hour for sure. And what do you say again? Okay? When y'all are talking about how muscular your cars are, what is the thing you usually refer to? Okay? But what number do you usually say? It'll do in something. What have you just said? You have said an acceleration. 0 to 60 is change of speed, change of velocity, in so many seconds. That's change of time. That's exactly what this was. This is just 60 to 80 kilometers per hour in 4 seconds. That was an acceleration. So when you're talking about, yeah, I'll do 0 to 60 in 4.2 seconds, you know, that's talking about acceleration. Okay? And you hear people talk about it all the time. You probably don't, but yeah, you hear people talk about it all the time. And that's a legitimate unit. Distance per time per time. The units don't have to be the same, especially if you change the speed in kilometers per hour in so many seconds. They're going to be hard to get in the same units, but that is an acceleration. Okay?
So we don't have to do all the crazy conversions with that?
With that one, I would say not, because you're either going to come up with some incredibly small or incredibly big number, and you think of change of speed in kilometers per hour, but it takes so many seconds to do it. So that's a reasonable unit for that. Now, sort of the SI, the standard, would be meters per second squared. That's your standard acceleration. But when you talk about cars, you don't measure it. You don't think in meters per second. You don't have your speedometer set up in meters per second. You have it in miles per hour, kilometers per hour. So yeah, you use that. Okay. Now, then they give some examples. The first second, you're when you started, you were at 60 kilometers per hour. 1 second later, you were at 65 because it increased 5 kilometers per hour per second. The next second, you were at 70. The next at 75. And the fourth second, you were at 80. It took you 4 seconds to get there. So it seemed like that was pretty redundant, but it's there. Now, let's play a little bit with the units. Okay? I mean, basically units. Okay, let's erase all that.
We should put it in miles per hour.
Second? Okay.
I'm saying I think we should put it in miles per hour.
Yeah. Actually, I didn't mean units. I meant parameters. Okay? What was the definition for acceleration? Does anyone remember? Change in velocity per unit time. That's a very good one. Now, if we do the delta, what does that delta usually stand for? Yeah? Well, how would we express that as 2? That would be V always final minus initial. Okay? Final velocity minus initial velocity. That's your change. Delta, difference, subtraction. Okay? Over the time interval, that may be T final minus T initial, or just the delta T, the time interval it took. Okay? So quite often they'll leave that as just time. Well, how much time did that take? And you'll just put the T. Okay? Okay? Now, given that, we can multiply both sides of this equation by T, and that'll wipe out your denominator there. Oh, shucks, no more fractions. And this will give you, I'll write it this way first. AT is equal to V final minus V initial. But I want to start with the V final, so I want to add V initial to both sides. And then you would have V final is equal to V initial plus AT. There is one of the equations we call a kinematic equation. Yes?
What does that say in the bottom left corner?
Right here?
Is
that what you meant? Huh?
Yeah, that one.
Okay. I added VI to both sides of the equation.
Okay.
So there, it wiped it out. Here you added AT, so I put it in front. VI plus AT.
Okay.
That's one of the equations we call a kinematic equation.
Okay.
Final velocity is equal. See, this is if you're, before I multiply by T, this is if you knew the others and looking for acceleration, this is what you would use. If you knew the acceleration, time, and initial speed, what's going to be your final speed? That would be the one you use. Same pieces of information, but some you know, some you don't, so you rearrange your equations. Literal equation. Okay? Now,
So that final equation says velocity final minus velocity initial plus AT.
Yeah. Okay, this thing right here.
No, the bottom right.
Right here?
Yeah.
This is the equal sign. My top part of the equal sign didn't show up too well. This is ionizing pen. I don't like with it too well. Okay. But V final is equal to the initial plus AT, which if you think about it, your final speed is your initial speed plus how much you're changing your speed over what time frame. So change of speed for change of time, that's how much you change your speed. So your final speed is your initial speed plus your change of speed. Yeah, that makes sense. Well, change of speed is acceleration times time. Okay. Which the acceleration is change of velocity for change of time. So multiply that by time and get change of velocity. Yeah. Okay. So let's do example 2.3. Let's erase this. Everybody got it? What you needed there? All right. A bicycle moves from rest. What does that mean, from rest?
From 0 miles per hour.
0 velocity. So your initial velocity is equal to 0. So when you see the term from rest, you can almost always say initial velocity is 0. Okay? You drop a ball. Okay, this will be a later thing. If you drop it, that means initially it wasn't moving, you literally started moving, so initial velocity is 0. Okay? Second?
But I feel like I'm back in physics.
That's exactly where you are. This is physics and chemistry. Okay? We're doing the physics part first, moving to chemistry. Okay? So from rest means initial velocity is 0. Okay? 5 meters per second. What you reckon that might be? That's your final velocity. Okay? Meters per second gives it away as a velocity. Okay? In 5 seconds. What's that? What's that? A time. Or your time interval, you could say delta t if you wanted to. Okay? So the question is, what is the acceleration? Think we can do it from what we were given? Yes, What was our formula for acceleration? It was just up there a short while ago.
A equals delta V.
Delta V
Over delta T.
over delta t. And what was delta V?
5 meters per second.
V final minus V initial. Delta is always final minus initial for whatever you're deltaing in. And this is velocity. Over, and the time interval was 5 seconds. Okay, well, what is your final velocity? 5 meters per second. Minus, what's your initial velocity? 0 meters per second. Okay, over the time interval of 5 seconds. So what's your acceleration? Say again? Okay, 5 meters per second, or 5 divided by 5? All right, that would be 1 meter per second. Yes.
Per second, okay. The T at the end. Is that the time?
Okay, I'm sorry. That was from here. I was running out of room, so I said 5 seconds is your time interval.
Okay.
That's what came down here. That, okay, separate. Okay, sorry. But good catch. Okay? So when you subtract 0 from 5, you still got 5, right? So you got 5 meters per second divided by 5 seconds. That would be 1 meter per second. Now we do have a little shorthand for that. Anyone know what that is? 1 meter per second squared, exactly. Even though no one has ever seen a square second. No, I'm sorry, that's this. Okay. We just call it that. Meter per second squared. Good deal. All right. That was example 2.3. All right. We clear this. Everybody got it? Okay, clear that, and let's do 2.4. An automobile uniformly accelerates. What does that mean? Constant acceleration. Very good. From rest. What does that mean? What 0? Initial velocity is equal to 0. Initial velocity from rest. It accelerates at 5 meters per second squared. What's that a measure of? The units help. Acceleration, of course. That's your it says accelerates from that accelerates at 5 meters per second squared for 6 seconds. What's that a measure of? That's your time interval, or delta t or t. Okay? The question here, what is your final velocity? How can we do that? And what is the equation? V final is equal to? Say again? Remember, we just had it up there.
What's the question?
What is the formula?
V final is equal to V initial.
The initial plus
Acceleration.
AT, your change of speed. Well, the V initial was 0, so that didn't add much, plus, what's your acceleration? 5 meters per second squared times, second?
6 seconds.
6 seconds. Notice your units are your friends here. The seconds, one of the seconds, the 1 second in the numerator cancels one of the ones in the denominator, and that leaves you with what number? Final velocity?
5 meters per second. 5 meters over 6 seconds.
What does it mean to write A times T?
30 meters.
It's what?
30
30. 30 what?
meters.
Per second. Very good. Like pulling teeth. I feel like a dentist. Okay. Now, the final velocity, and that's exactly a good unit for velocities, meters per second. So the final velocity is 30 meters per second. Now, 5 meters per second squared acceleration sure doesn't sound like much. How long do you think you could keep that up?
I don't even know how fast it is.
It's not a fast, it's an acceleration. You're accelerating 5 meters per second every second. And guess what? In very short time, I don't think you could do it for 10 seconds. Because soon you're going so fast, nah, not going to happen. So usually accelerations are fairly small. And you don't usually do them for very long time periods. Yeah.
Okay, you lost me there. But, so what we were trying to do in that equation was find the final velocity?
Yes, exactly.
Okay.
That's why we set it over here by itself. It's initial velocity plus acceleration times time. Acceleration times time, meters per second squared, times seconds would be meters per second. This is meters per second. That's meters per second. Sure enough, units are your friends. Be kind to them. Make sense? No? Okay.
It's the same formula, but you use it differently.
Yes, exactly. Right. Okay. Remember, for your test, you can have formula and equation sheets. I would definitely use those babies, okay? Okay. Now, in reality on your test, now this first test we have will have several calculations. Probably, not, this isn't this. This is the ones we did first. Density, volumes, pressures, that kind of stuff. Not that much, okay, but you'll have several calculations. All subsequent tests, this chapter and after this, mostly multiple choice with only a few calculations. But do the calculations. Make sure you can get those, okay? All right. And sure enough, the book gave you 30 meters per second. All right, before we move too much further, at the top of page 31, there's Science and Society, Transportation and the Environment. Pretty interesting little blurb there, okay? Not really where we want to do a lot of thinking, okay? But we really do need to start thinking on these kind of terms. Now, of course, here in the U.S., we're all spread out. We're a huge country. But over in Europe, where a lot of the countries are really small and concentrated population centers and stuff, people do. I'm trying to think which country it is. Seems like it may be Denmark. No, Netherlands maybe. One of those countries, way more people ride bikes than drive cars. Way more. And man, the people are healthier, the air is cleaner, the whole country's better off. But they don't travel such large distances as we do. Yes?
Okay, I'm just looking over my equations. So
Okay.
Is the equation different for speed versus like average speed? Are those two different equations? Because I have this one, it has the bar V or whatever, and our average speed equals final velocity plus initial velocity divided by 2.
Okay. Okay, let's go back to that. It's a good question. No. Okay. Here's one. I said before, say it again, we'll use it in lab. One way to calculate average velocity is distance divided by time. Right there. Okay? That's it. Average velocity is distance divided by time. That's one way to get an average velocity. If you know distance, you know time, you can calculate your average velocity that way. However, there is another one, and this works only for uniform accelerations. With uniform acceleration, then you have another average velocity. And that is final plus initial divided by 2.
So that's the uniform, not, okay.
But yeah, it's uniform acceleration gives you another way to calculate the average velocity.
So it doesn't.
What's that?
I don't know, never mind. I don't want to ask you to make sense.
No.
So you can use both of them.
Well, yeah, it depends on what. If you know you got uniform acceleration, and all you have is initial velocity and final velocity, this is the way to get your average velocity.
Right.
However, if you know how far you traveled and how long it took, use the other one. So use what fits. Were you Marine Corps? Okay. Did you ever go to very many Navy schools? Probably not. Navy schools were not bad. They're not top of the line probably, but not bad. But one thing they said in every Navy school that I ever attended, and they sent us to schools all the time, there's no such thing as a dumb question. Except, there is one exception. One you don't ask. Because if you have a question and don't ask it, that makes it a dumb question. If you have a question and ask it, that's a legitimate question. So please, don't ever hesitate to ask questions. Because they never said that in Marine schools either? He doesn't want to admit it, but they are related. Okay, never mind. Yes?
Can we take a break?
We can. It's 25 till 5, right? We will be breaking for lab at 5:15, but yeah, we can take one now. That may give me a chance to call. Well, before we take the break, let me ask the question. I hate to ask this because I don't want to impose on anyone, but does anyone head toward the east after this is all over with tonight?
I tell you what, I always take.
No. I don't want anyone going out of the way. Because I want to go out of the way, I'll make my wife go out of her way. But, what's that?
I'm going to Pleasant Grove. Is that where you're coming out?
Yeah, that's in that direction.
Okay. What you need me to do?
Huh?
What you need me to do?
Okay. See, I don't have a car. The part wasn't in, so I'm without a car today. So I need a ride. But if you get me to Pleasant Grove, then my wife can meet us at Pleasant Grove.
That's fine.
Okay. Where would be well, we'll talk about that later. Anyone going any further east than Pleasant Grove? Okay.
East is like towards Tuscaloosa.
No, west is Tuscaloosa, east is toward Birmingham. Anyone heading? You're going to Tarrant? Would you mind giving me a ride as far as, well, I live in Southside, Birmingham. Forest Park.
I'll take the car.
What's that? Okay.
I'll take his car.
Okay. We'll work that out. I have my cell phone. I'll call my wife and tell her where to meet. Okay. Well, thank you. He goes a little further.
I was going to kidnap you anyway.
Okay. Okay. I saved you. I saved you then. Yeah. Okay. All right. I eat an awful lot, so never mind. Okay. All right. Let's take a quick. Try to keep it 5 minutes or less. Break.
Yeah.
All right, we had gotten to page 31. We had already had the slides on it, but I forgot to do the examples. So let's do example 2.5. That's the bottom right-hand column of 31, on page 31. An automobile, and this is just below that equation someone was asking about, V bar is equal to V final plus V initial divided by 2. An automobile moving at 25 meters per second. 25 meters per second. What would that be a measure of? That's 25.0. Yeah, that's a velocity. Now, it doesn't say what. Oh, yes, it does. Well, sort of does. Then comes to a stop. So it starts off moving at 25.0 meters per second. What would that be? That would be your initial velocity. Comes to a stop. What does that mean? Say again? Final velocity would be what?
0.
0, because it came to a stop. It's no longer moving. Okay? In 10 seconds, what's that a measure of? That's your time interval, or delta t if you want to call it that. Okay? When the driver slams on brakes. Okay? How far, so what are we looking for? Distance. How far did the car travel while stopping? Say again?
2.5 meters.
I can't hear you.
2.5 meters.
Okay, how did you get that?
Divide by 10.
Okay. Let's see. What's our formula?
The formula.
Distance equals initial final velocity plus initial velocity divided by 2. Is that it?
Okay. You might recognize it better if we started this way. V bar is equal to distance over time, right? Would you recognize that one?
Yeah.
Okay. Now, here's the thing. When the driver slams on the brakes, he's probably not pumping them. He's probably not, alternating or something. He just slammed on the brakes. We're going to assume that's uniform acceleration. A uniform force, which would be a uniform acceleration. We haven't gotten there yet, but that's our assumption. That it's not something that's varying with time, that he's accelerating, or in this case, decelerating at a uniform rate. That's our assumption. Now remember what else V bar was. In fact, I mentioned, there it is. You might not be able to read it too well. What's that?
Looks like it says
V final plus V initial over 2. Someone just asked about that, right? That is when you have uniform acceleration, you can also use that one. So what we've got here is you got initial, you got final, so your V bar is what was that last one? Oops, too much. Went the wrong way. V final plus V initial divided by 2. V final was 0. V initial was 25.0 meters per second. Divide that by 2, and what do you get? Average speed or average velocity is, say again?
12.5 meters.
12.5 meters. 12.5 meters per second. Now that's meters per second, not meters, okay? That's average velocity. But now up here you have average velocity is distance divided by time. So the distance, that's what we're looking for, would be V bar times time. Multiply both sides of this by time, and that gives you distance. So now we got our average velocity, 12.5 meters per second. Multiply that by the 10-second time interval, right? So what would that give us? 125 meters, because the seconds cancel out. Sure enough, 125 meters. Let's see what they got. Yes, 125 meters.
What happened after we got to 12.5 meters then?
Okay. Remember I said you can use both of these formulas and use them with each other. Okay? What they gave you to begin with was the initial velocity and the final velocity, and they also gave you time. Okay? Now, you're looking for distance, though, in that time. How far did it travel in that time? Well, you use the initial and final velocity here, since you're assuming uniform acceleration. Add those together, that gives you 25. Divide by 2, that's an average, 12.5 meters per second. Okay? That's your average velocity. Once you have the average velocity, use this formula, average velocity is distance over time, or distance is equal average velocity times time, and then you have your 12.5 times your time interval, 10 seconds. That gave you 125. Okay? Make sense?
Yes.
Sorry, it's all over the board. I just don't have a lot of room to write. Okay? Now, I don't want to erase all that, but I'm going to erase parts of it. Okay? Because the example 2.6 is building on this. I don't think we need this anymore. We already calculated that. I don't think we need that. If we need it, I'll write it back down again. Okay. Okay, there we go. Example 2.6, what was the deceleration of the automobile in example 2.5? Well, what is your formula for acceleration? Anyone remember that one? V final minus V initial over time. What's your V final? 0 minus V initial. What's V initial? 25.0 meters per second divided by 10.0 seconds. And what does that give you? The 0 doesn't contribute anything there, so you can just basically throw that away. That's throwing nothing away, okay? Negative 2.50. You need 3 significant digits, remember? 2.50 meters per second, or you can write that as meters per second squared. So there was the average acceleration when you slammed, deceleration in this case, or negative acceleration when you slammed on brakes. Okay? So what was the deceleration of the automobile? Negative 2.50 meters per second squared, or meters per second to second if you prefer that. All right, good deal. Any questions on those? Okay. These formulas are your friends. Okay, hang on to them. Get used to them. At the end of the chapter, you'll find the, oh boy, what do they call it? There's several things at the end of the chapter. One of them is parallel exercises. The group A parallel exercises are a lot like your examples, and that's the group A ones have answers in the back of the book. So if these, if you're a little fuzzy about those, use those group A parallel exercises at the end. But realize that, not but a few questions are going to be, after the first test, not but a few questions are going to be calculation-wise. You will need to know some, but not that many. Most of them will be multiple choice, like the concept questions, conceptual questions. Yes?
Like, how many questions require the equations? Is it like half equations?
How many what? I'm kidding you.
How many of the questions on the test will be equations? Is it like half equations and half multiple choice, or?
Okay. The first test is quite a few calculations, but it's just one equation. I mean, just manipulate three different ways like we did in class, okay? And it's the density is equal to mass per unit volume, or mass is equal to density times volume, or volume is equal to mass divided by density. Those three equations, you can get all from the other, and you use those however you need to. There's probably, I'm guessing maybe 6, 7, or something like that you actually do calculations, okay? And that actually is 2 questions with 3 parts each, or something like that. There may be 1 or 2 more, but not that many. There are some that are multiple choice on the first test, and there's a few that are fill in the blank on the first test, okay? So it's a variety of things on the first test, okay? The second and all subsequent tests, chapter tests, are mostly multiple choice, and only no more than 2 or 3 problems, and maybe 1 or 2 fill in the blanks. It varies from test to test, okay? But most of the tests after the first test is mostly multiple choice. A lot like the last one, whereas Physical Science 111, mostly multiple choice with 1 or 2 or 3 sometimes fill in the blanks. Well, some of those will be fill in the blanks and some of them will be problems. About like that. Okay. All right. Any other questions? Okay. So let's now move to forces. Basically what we've done in the first part of this chapter is describe motion. We describe it with distance, with displacement, with time, with velocities, with acceleration. That's describing motion. The formulas help you tie those together. This part of the chapter is forces, and this is explaining the motion. Why did the motion occur? Okay? So we'll start with a little bit of historical background. And we start with good old Aristotle. Way back, BC, what was it, maybe 200 BC or something like that. Way back there. What he did, and we've mentioned them several times when we talked about scientific methods, he made the observations, heavier objects fall faster than light objects. That was his observation. So everybody said, Aristotle said it, I believe it, yep, we'll go with that. Okay? So for millennia, thousands of years, people said, yeah, heavy objects fall faster than light objects. Okay? He also said, objects moving horizontally require constantly applied force for them to keep moving. Sure seemed like it to him. He couldn't just push a car, he didn't have a car, but push a cart and it just continue rolling forever. It wouldn't. It would stop. You have to keep pushing. So he observed these things. Okay? He relied on thinking alone. He observed things and said, yeah. He never experimented. Not that I can ever tell him he did. Okay? That was before the scientific method. Now let's take that first one. This is just sort of a dumb illustration of that, and I don't know if I have anything I can use. Yeah. All right, now this isn't exactly an experiment on this first one, but it's somewhat similar. Here I have 2 pieces of paper. Would you assume that the 2 pieces of paper had about the same weight?
Yes.
Okay, assume that, right?
Yes.
So that means they should fall at the same rate,
Yes.
according to Aristotle, right?
Yes.
Right? Okay, got it?
Yes.
Huh?
Well, I was gonna tell you. We already
Was it heavier? Is that why it fell faster?
No.
No, it had.
object.
Huh?
Smaller.
Yes, it had nothing really to do with the heaviness of it. It had to do with things like surface area and how big it was. Yeah, it didn't have anything to do with heaviness. So he never experimented on it. He just observed, said, "Yeah, looks like heavy objects fall faster than light objects." No, these weighed the same thing. According to him, they should have fallen at the same rate. Obviously, they didn't. Okay. So, other things like this, he was off a little bit on. Well, here came Galileo and Newton. Now, pretty odd thing. Galileo died either the same year, I think it was the same year that Newton was born. So they never met each other. It was later in the year. Of course, Galileo was in Italy, the old dude there, and Newton the baby up in England, so never were they to meet. But it's sort of like cosmically they were a tag team, Okay, I get my part, you take over from here. No, I'm just kidding. Okay? Galileo and Newton came along and basically said all objects fall at the same rate. If you control for size, surface area, and things like this, all objects really do fall at the same rate. And we'll see why. Okay? No force is required for uniform horizontal motion if you take out friction. Okay? And they did experiments and showed with no friction or very minimized friction, no force is required. Okay? And they did their reasoning based on measurements, experiments, testing different theories and hypotheses to see if they work. This is the historical background of forces. Okay? You see, Aristotle had problems. He had to split all materials into two different kinds. He said, well, on the earth, he called them terrestrial laws, and then in the heavens he had celestial laws, and they were different. And Galileo and Newton, everyone since then, and said, no, these laws are the same. It's just how you have to look at them, apply them, and take things into cases. Okay? So let's look at forces. I can remember, did anyone need that last slide up there longer? I'm sorry, did I go too fast? Did anyone need it longer? No? You got it, everybody? Okay. All right. I can remember I took physical science in high school, 9th grade, and I had the high school football coach, Huey Hubert, okay? He was an old single-wing something or another. Yes.
How do you spell Pooey?
Pooey? I think it was Pooley or something like that. It was a nickname, okay? I don't know what it stood for, but nobody ever made fun of him. He was one mean character. I mean, he was meaner than Bear Bryant before Bear Bryant was. I mean, he played football at Alabama. He was on either the receiving or the throwing end of the longest pass recorded in Rose Bowl history for many years. It may still be on the thing. He was one mean character. Okay, and I can remember, and he talked just like Bear Bryant. A force is a push or a pull. He had gravel in his mouth, and you didn't argue with him. Okay. And I remember, and that's exactly a pretty good definition of force. A push or a pull capable of changing an object's state of motion. It may not always change the state of motion. I'm going to push on the desk. Most of the time I wasn't changing the motion. It sort of stuck to the floor there, but I was still exerting a force on it. But it's capable of changing. If I just greased that a little bit, it would have moved pretty easily. Okay? So a push or a pull capable of changing an object's state of motion. Overall effect is determined by the vector sum, not just adding the magnitudes, but the vector sum of all the forces. That's called the net force on the object. here's an example. Here's we have, this looks like a container ship of some nature. And let's say we have a couple of tugs come here, and they're pushing on this side of the ship, and pushing it with 1,000 units of force to the east. What's the net force on that ship? 2,000 units of force to the east. Okay? Well, what if the tugs got their wires crossed, and one of them came up on this side of the ship, and one came on the other side, didn't know the other was there, and they both started pushing with 1,000 units of force each? Zero. There's lots of force on the ship, but the net force is zero because it's a vector addition. Okay? What if, however, the big tug pushed from the east side, pushing to the west, whereas the little tug was over here pushing on the west side, pushing toward the east, and the little tug was exerting 1,000 units of force. The big tug was pushing with 2,000 units of force. The little tug was saying, what's going on here? The net force is 1,000 units to the west. Vector addition, not scalar addition. You can't just add 1,000 to 2,000 and get 3,000. No. East, west, the 1,000 each cancel each other out, left with 1,000.
So, but on that last one, if they said scalar, it would be 2,000.
Yeah, if you were trying to add something scalar quantities, yes, you just do that. Now I have another example, and this we experienced that when we bought the house where we currently live. There were a couple of great big old, well, there are two huge pine trees in our side yard, but there were two little spindly, crooked pine trees that had tried to grow up under the canopy of the oaks and the other trees there, and they were ugly. Now, I don't know why the previous owners had left them there, but anyway, my wife wanted them out. Well, at that time I didn't have a chainsaw yet, but my father-in-law did. So he and my brother-in-law came down from Huntsville, and they helped us take down the trees. So he brought with him a pretty long rope. We threw it up as high as we could, looping it over one of the branches somewhere way up there. And then Dan, my brother-in-law, and I were going to pull on the rope while my father-in-law operated the chainsaw, because we had lots of other plants in the yard, and we didn't want the tree just falling anywhere. We wanted to sort of guide it down where we wanted to go. Now, to get the maximum net force, we would have pulled together, right? Looped around the tree and pulled together. That would have given us the greatest net force. Would that have been a smart move?
No.
Why not?
Because it would have fallen.
Yeah, it would have fallen right on top of both of us. So what we did, he pulled this way and I pulled that way. Our net force was not as great because, you see, the forces we were pulling were like this. There was one component of the force this way and another that way. He was pulling this, one component this way, the other that way. These two components canceled each other out. We were pulling against each other, so to speak, a little bit. But the net force was these two components in the middle. They added together. And therefore, we could get the tree to come down in between us in the direction we wanted it to go. That's using vectors. Okay? Have you ever, my younger brother worked, he's retired now, for electric power company, a rural electric power company near where we live in Georgia. And he always looked at power lines, I mean, all the time. So I guess it rubbed off and I started looking at power lines. And have you ever noticed the power lines, especially when we go up to Winston County, and those roads do like this, and so the power lines are along the side of the road, but they're having to go like this too. And every time they change direction, they have to have a guy wire here to keep the pole from falling across the road. And those are forces. Force holding it here, the wires are pulling it this way and that way, you know, in the bend, but you have to have a guy wire to keep it up straight. You don't have it, the pole bends, may actually fall, okay? Those are all vectors. We use them all the time, most of the time not even realizing. Net force, we want the net force on that power pole to be what? Zero. You don't want it moving in any direction. You want it to stay right there. So you set up the guy wire so you get a net force of 0. Okay. This slide's talking about the whoa, look at what you did. You let me go right past 5:15, didn't you? 5:15, we're supposed to stop the...
I thought it was 5:45.
Okay, but we're having the test today. So the test is the last 30 minutes, so that gets us to 7:15. So we're supposed to have started the lab. Sorry about that, but we will start with fundamental forces next time. Okay? Usually, say again?
We can do the test next class.
I thought that was the idea, because let's get no books.
Okay. Y'all want to do that?
Yeah.
Yes.
Yes.
What?
Yes.
What?
Okay.
You can try to ask.
Okay. Actually, it says many of you are not going to be taking it. Now, the books are supposed to be in either late today or tomorrow. That means if you want to take the test on Thursday, you better get your book today or tomorrow, which probably means tomorrow, because bookstore, I think, will be closed by the time we finish here. They weren't there before class. I went down to check right before class to make sure. And guess what? They had put more physics books up in the thing. And I went, look, I'd already told her. He said, no, these are books. I said, no, those are the wrong books. So I said, do you still want these there? He said, oh, no, I'll have removed those. Well, I told him that last time, and he still had them there. So I don't know. But anyway, we'll start with the fundamental forces next time. All right, let's end the slideshow, but I'm not going to end the screencast-o-matic. But what I'm going to have to do is give y'all another break while I set up the lab. It won't take a super long time to set it up, but so let's go on with the thing, and we'll do the lab at 5:45. Okay, sorry. I thought we had talked myself into it, and then I talked myself out of it. Okay, let's get the... Oh, goodness, here we go. Sorry about that. Chapter 2. Okay. Here it comes. Sorry about this. Welcome back. Slide 7. That's where we left off last time. This is not a good package here. All right, here we go. Fundamental forces from current slide. Now, yeah.
So does that mean we're going to have the test on Thursday? The first chapter and the second chapter?
You said the chapter.
Okay, time out. Okay. We're not anywhere close to finishing chapter 2. So certainly we're not having a test on chapter 2 on Thursday. We're only having the test on chapter 1. It was scheduled for today, but because they don't have the books, then we're going to have it Thursday. Okay? We are going to do a lab on chapter 2 today. If we get far enough Thursday, we may have another lab on this same chapter 2 on Thursday, and then have the test. If we don't get far enough, then we'll not, but we'll go as far as we can. All right. So let's get back. Fundamental forces. Okay? The most of all basic interactions can be characterized according to these 4 forces. We only deal with 2 of them most of the time. Okay? The others are there, we just don't usually deal with them. The first of these is gravitational force. Gravitational force is a mass interaction. 2 objects, any 2 objects with mass, and all objects have some mass, they interact with each other, it's always attractive. Always masses are attracting an object. This is what has the planets moving around the sun, the Earth, the moon moving around the Earth, the stars moving around the center of the galaxy, local star units, moving around their center of mass. This is what keeps everything like this moving, gravitational forces. Now, gravitational forces of these 4 forces are actually the weakest of these 4 forces. However, they go the greatest distances. I mean, they reach across the Milky Way, which is, what was it, 100,000, 100 million?
A lot.
Yeah, light years. I mean, it's a lot. It's huge. Okay. Now, next strongest, gravitational are fairly weak, but they go a long distance. Electromagnetic forces, these are charge interactions, not mass interactions. You have positive charges and negative charges, or positive charges and positive charges, or negative charges and negative charges. They all interact. And this is what electricity is based on. It's also what magnetism, yes.
Did you start your thing back up?
Yeah. Oh, yeah, you don't get to see it. Yeah, it's running. I turned it back. Thanks for checking. Yes.
Sure.
So magnetism, that's magnets, right?
Right.
So they're electricity and magnets are very close together?
Very close together. Closer than you ever imagined. Okay? And when we get to chapter 6, we'll be doing an experiment showing that. Okay? So something to look forward to. Okay? But yeah, they're very closely related. What's happening there, atoms, molecules, and most of chemistry is based on this electromagnetic attraction. Okay? I said you could have two positive charges. What happens with those? They repel. They don't attract. A positive and a negative, they attract. Or a negative and positive, they attract. But two negatives, they repel. So gravitational forces are always attractive. Electromagnetic forces may be either attractive or repulsive. Okay? And most of what happens in atoms, molecules, and chemistry are, a lot of that has to do with electromagnetic forces. Okay? Now, these are much stronger than these, but they call them weak forces. They're involved in certain nuclear reactions. So we don't deal with these every day, okay? Let's hope we don't anyway. These are the forces that hold atoms together, okay? Not electromagnetic. Those hold molecules together. Weak forces are basically involved with certain nuclear reactions. That's all they say about it. You can read the book. They may say a few more sentences. Then the strong forces. Now let's think back. Let's get back to electromagnetic. Is it really true they're stronger than gravitational? Have you ever seen the experiment where someone with fairly clean hair, not oily hair, combs his hair with a nylon brush, if they got some hair, okay. But, combs the hair and then reaches down and holds it over some little strips of paper, and it picks up the pieces of paper. You seen that? Okay.
It sounds familiar.
Yeah, okay. And you've probably seen a gal on a Van de Graaff machine with her hand here and being electrolyzed, and her hair stands up. Well, guess what? The hair, gravity would be pulling the hair down. The electromagnetic forces are putting it up, or picking up those pieces of thing. Gravity's still pulling down, so the electromagnetic forces are actually stronger than gravity. Yes?
Wasn't the last experiment that you mentioned with the
Van de Graaff machine?
Van de Graaff machine, wasn't it Nikola Tesla that invented that? Because I remember reading about when he did the current.
He laid the groundwork for it. Van de Graaff actually created that machine, but Nikola Tesla laid the groundwork that Van de Graaff built on. So they are related, very, very close. Okay, now, so here we have electromagnetic forces being stronger than gravitational. However, electromagnetic forces don't reach nearly as far as gravitational. Gravitational forces reach across galaxies, okay? Electromagnetic forces have to be pretty close. Like when you comb the hair, if you hold it here, you're not going to move those at all. You have to get really close, and then it overcomes the gravitational force. Now, let's think about a nucleus of an atom? What's a nucleus made of? Anyone know? Protons and neutrons. What are protons, by the way? Positively charged particles. Very positively charged particles. Okay? And neutrons have no charge. So here you have a whole bunch of positively charged protons with quite a few neutrally charged neutrons, but they are held together in just about the densest thing known to man, the nucleus of an atom. Now, if these positive charges tend to repel each other like crazy, much stronger in gravitational, then what holds nuclei together? There aren't any negative charges in there, folks. There has to be some strong force that completely overpowers the electromagnetic forces. But they don't go very far. But in that dense little nucleus, they hold them together very, very tightly. So that's why they're actually stronger than electromagnetic, because they overpower the repulsion that protons have for each other and holds them together very, very tightly. Okay? The weak forces are in between those two. So that's just a little bit of sort of an aside on forces. Now let's start dealing with forces. We're going to start with horizontal motion, and it says on land. It doesn't have to be on land. It's just horizontal motion, which means you don't have any vertical component in it. And basically what we're going to have to begin with is straight line horizontal motion. We're not going to let it curve. We're not going to let it bend and change direction. Okay, so here's what we have, and this was part of Aristotle's misrepresentation, the thing he didn't take into account. If you roll a ball across the floor, okay, as long as you don't roll it too fast, over time it will stop. Okay? But the reason it stops is that you exerted a force on the ball when you started it rolling, but now after your hand, let's say it's a bowling ball, okay? And after your hand, that leaves your hand, you exert no more force on it. So you are adding no more force in that direction. However, I'm sorry, I should be doing it this way. You roll it this way, but you have air that it's having to bump into. You have friction with the floor that it's having to overcome. And as long as those two sources of forces are there, you can't exert any more in that direction. Both of those are pushing in this direction, so ultimately the ball does stop. Okay? And that's why Aristotle said you have to constantly apply motion for a ball to keep moving. Okay? But you really don't if you can control for these resistive forces. Because the net force on the ball, once it leaves your hand, is zero. The applied force is zero. The net force is the sum of these two resistive forces. And why we call them resistive forces? They always are moving against the motion of the ball. The ball's coming this way, so it's bumping into air molecules, and you don't think that's a lot, do you? But it is. And the friction on the floor. And listen to it. When you roll that ball on the floor, you can hear it. What are you hearing? You're hearing vibrations from friction of the ball and the floor interacting. If it was getting there perfectly lubricated, you wouldn't hear any sound at all. Okay? So the net force is actually against that. That's why the ball stops moving. However, if you did like Aristotle said, you constantly apply a motion. How you do that, I'm not sure. Maybe you're behind it, blowing on it. Have you ever watched that weird Olympic competition in the Winter Olympics?
Curling?
Yes, curling. Oh, wow. Isn't that strange? Somebody's there sweeping in front of it. Just, one person is given a thing and they're trying to diminish the air resistance and the frictional resistance as much as they can, trying to encourage that to go. Okay? Well, they have no more applied force, they're just trying to minimize these. Okay. So the natural motion question, back that Aristotle raised, is a continuous force needed to keep an object moving? No, if you have no unbalanced retarding forces. If you can control from them, no, it can keep moving. Okay? But if you have those, yeah, it's going to stop because there are unbalanced forces there. Now, another concept here, inertia. If you hear the term inertia, what comes to mind? Anything? Inertia. What I usually think of, what are the first 5 letters of inertia? Inert, meaning nothing. I think couch potato, not moving, just there. Okay. That's part of inertia, but it's not all of inertia. Inertia is the measure of an object's tendency to resist changes in its motion, including rest. That's the inert couch potato. You have to do some sort of force to get it to move, okay? Okay, it tends to resist any tendency to change its lack of motion, okay? But the same's true of something in motion. If I were to roll a bowling ball as fast as I could toward you, either you're going to move or you got to get the ball to stop moving, and both of those are going to require, you're going to have to resist changes because that bowling ball has a lot of inertia in its motion, okay? Similarly, if the bowling ball is at rest and I want it to move and I kicked it, not going to feel too good, okay? It's going to require a lot of effort to change that motion from rest to moving. Whereas, if that was a ping pong ball I rolled across the floor, yeah, I can handle that with no problem. Or kicking the ping pong ball, yeah, it's going to move without any pain on my foot at all because it doesn't have as much inertia. So inertia is highly related to mass. Bowling balls have a lot more mass than ping pong balls, okay? And that's what you're dealing with. Was there a question or just, okay? Okay?
Okay, I feel like I remember learning this when I was like a kid.
You did learn it, or? Yeah.
Was inertia the example that they use when you're riding the car? And
Yes,
on the brake,
exactly.
Okay.
Boy, she's psychotic. I mean psychic. She knows what we're going to do next, okay? We'll actually have that as an example, okay? Coming up. Not quite there yet. So let's talk about balanced and unbalanced forces. Motion continues unchanged without unbalanced forces. Boy, there's a lot of negatives in there. Unchanged without unbalanced. Ugh, I'm getting confused here. Motion continues without change, unchanged, as long as you don't have unbalanced forces. As long as all your forces are balanced, motion continues unchanged. Okay? Here's another example, not quite the bus example yet. Here's an airplane flying at 500 miles per hour. Straight level flight, 500 miles per hour. What's the net force acting on that airplane? Say again? What's the net force acting on the airplane?
Oh, the net force.
What's the net force acting on the airplane? Straight level flight, 500 miles per hour. Say again?
Gravity.
Okay, certainly gravity is pulling the plane downward. But, remember this. Remember that one? Bernoulli's force. I could tell the bead was coming there, right? Okay. Yeah, sure. Bernoulli's force is giving it lift. Because remember how those airplane wings are formed? They're fat on the outer edge, and they taper off down here. They're also slanted, so the force on the bottom side of the wing is greater than on the top. But on the top, the air has to go farther in the same time, so that for it goes much faster. The greater the velocity, the more the lift. So, for every force of gravity down, there's equal and opposite lift from Bernoulli's force upward. Okay? Someone mentioned air resistance. Yeah. Going at 500 miles per hour, there's a lot of air resistance on that plane, right? But guess what? He's got jets that are firing, exhaust out the back. That's pushing it forward. So for every downward force, there's an upward force. For every right force, there's a left force. If it's traveling at level flight, 500 constant speed, no acceleration, then there is no net force. Okay? Hard to think of, but it is. Here we are in outer space. Okay? A satellite up there. No air resistance at all. None. Okay? The natural motion in free space is constant velocity. And that, remember I told you, Aristotle said, oh wait, no, you have to have one set of rules for celestial bodies, another set of rules for terrestrial bodies. No, it's the same set of rules, it's just with celestial, you have no resistance, no air resistance at all. So the natural motion in free space is constant velocity. But if this is indeed a satellite going around the Earth, guess what? It's always falling. It's almost time, isn't it? Okay? Always falling, yes.
Okay. Last semester, when we went to the
planetarium?
Yeah, and remember he was talking about the space air, whatever, that wore down Mars' atmosphere?
Yeah.
Does that not apply to outer space too? You said there was no air.
Okay. Yeah.
That gives the friction or whatever, slows down the force.
Right. Okay. Mars does have a little bit of atmosphere. It's not no atmosphere.
So that's that.
Yes.
Okay.
The moon basically has none. Mercury has basically none. Very, very little, not enough to give you any air resistance. Mars has a little bit of atmosphere. Earth has a good amount of atmosphere. Venus has an enormous atmosphere, okay? Very dense. Okay, so yeah, okay. All right, so natural motion in free space is constant velocity. As long as you're not changing direction, going in a straight line. Okay? Now, what if you wanted to slow that down some? You fire a retro rocket to slow that down. You have to apply a force to change its velocity. You don't always have to do that on Earth, but you do out there in space. However, if you wanted it to go faster, then you boost it. You fire the rocket in the other direction to make it increase. You stop firing the rocket, now it goes at that new speed, and it doesn't change that speed at all until it bumps into something, right? Okay? If, however, it was moving in this direction and you exert a force perpendicular, what's that going to do? Change its direction. Doesn't change its speed, either increase or decrease, it changes its direction. And that's what a perpendicular force is. It's still changing its velocity, just not changing its speed. The first one here was slowing it down, this one is speeding it up, this one changes its direction. But it requires a force to change, and it requires an unbalanced force to change the motion of that object. Okay? Now, that's probably a fairly good place to stop. Mention one other thing here. There's myths, mistakes, and misunderstandings. Not very important, but I remember a friend of mine was in a calculus class at Georgia Tech, and the professor actually gave them this problem to calculate. It was a bearable problem, but is it better to walk or run in the rain? Which do you get wetter doing? Second? Okay, it all depends on if you're running and you're running from shelter to shelter, then you're in the rain less time, so you actually get less wet. But the distribution of the rain, you're probably going to get wetter on the front and not very wet on the back because you're running into the rain. So it depends on what you're trying to measure. But if you're running and walking and you're going to stay there the same length of time, you're going to get just as wet either way. So that's the mistakes and misunderstanding. We'll start next time with falling objects. Okay? Now, just to give you a preview, on the following objects, we're going to do and follow that with compound motion. That's 2.4 and 2.5. If we finish 2.5 before the 5:15 on Thursday, then we will have another lab on compound motion, and then we'll have our test the last 30 minutes. Y'all are okay with having the test the last 30 minutes on Thursday? Okay. Because it's going to be a while before we have the Chapter 2 test, so I think you'll be okay. All right, then I'll end the slideshow again. Are there any questions? I'm going to pause. Screen cap. Do you? Right? Do you have the mass of the container?
Yes.
Okay. The person who was asking me, you have the mass of the container?
Yes.
Okay, you have the mass of the container and the water?
Yes.
Okay. The difference between those two is the mass of the water. Right?
No, but it's a ratio.
Is she talking about the last one?
Okay.
The last question, number 10?
Okay. Again, ratio of mass of water, that to the measured volume of water. That. This divided by that. Okay. Now, are we finally ready to start tonight's lab? Okay, now we have 3 teams. I have to mark roll again. I forgot that. Yeah.
Bye. Again. I hope he's not recording still.
I have it here. I didn't see it. Okay. Need to call roll again, so hold on just a second. Oh man, okay. All right, Rachel's still here. John. Okay, I'll see you. Got it. Chris Davis. Got it, thank you. Yale, I saw you. There you are. Okay. Thomas, I saw you too. Yeah, there you are. Okay, you're up here. Okay. Bo. I see you. Okay. Sean didn't make it in today, right? Okay. Justin's still here, right? Yep, got it. Eric? Okay, yeah, there you are. You're behind the box there, I saw you. Okay. Thomas? Did we lose Thomas? He's not back here? Okay, Andrew. Yeah, there you are. I saw you. So we lost Thomas, right? Oh, there he is. There you are. Right.
There's only one Thomas. You called 2.
Okay, I didn't hear anything on the first one, so I called. Okay. Which is Thomas?
I'm Thomas.
Okay, wait. I thought you raised your hand when I called.
You called Thomas. This is the second time you called Thomas.
Oh, wait, there's 2 Thomases.
There's not.
Okay. Thomas here and Thomas Keller. Huh?
That's his middle name.
Oh, but you don't go by that? You go by Ashton? Yeah. Okay, well, for some reason I circled Thomas. Sorry. Okay. All right. And Chris Lynn is here. David Lockhart. Yeah, got it. Chelsea's still here, right? Yeah. Alex. There you are. Okay. And Euryssi, I saw you here, right? You're my right. Where are you? There you are. Okay. Melva's still here. Samuel's still here. Somewhere I saw you walking around.
There he is, right
There he
here.
is. Got it. Okay. Angel?
Here.
Yeah, I see you. Lisa's still here. Okay, Scotty didn't make it in today, right? Okay. Adam? There you are. Got it. Ashlyn's still here? Or is she? There you are. Okay. Kedrick's still here. I saw you just a minute ago. Oh, there you are. Okay. And Jared is here. Okay. That's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. 3, 7, 11, 15, 17, 18, 20, 23. Okay, so with 23 people, 3 stations, that's 8 people per station, only have 7. Okay, so you got 1, 2, 3, 4, 5, 6 here. We need 1 more over here. 1, 2, 3, 4, 5, 6. No, you can stay. You're okay. One of you needs to go to the last station, and one goes to go to the middle station. And I guess 1, 2, 3, 4, 5, 6, 7, 8. Yeah. Yeah, 2 of you go to the middle station. 2, 4, 6. Yeah, 2 of you to this station, and 1
We gotta go to the
last
middle
station.
station. The 2 to the middle, 1 to the back.
Yeah, 2 people here, and 1 person back.
See ya. I'm not really going too far though, but
Yeah. 1 person here and 1 person there.
where does the other person go?
All right. Now I didn't bring. Okay, I'm supposed to be standing where I can record this. Okay. Yeah, go to the middle station back there. Okay. Now we got 3 teams. We only got 2 scales, but each team should have 3 balls. Okay. Now, when you're taking your measurements, if you zero the scale, okay, you zero the scale, okay, and put this on. If it'll stay on without rolling off, you can measure that way. If it tends to roll off, put this on, but then you have to zero with this and that on. Okay? Okay? You measure off. Wait, you already have. Okay. You got 3. Okay. Did y'all hear? Okay. Who has the other measuring pin? Who has the other big circle? So again, I don't know if you heard or not. Once you zero the scale, if you put this on and can measure it with that, you can do that. If they tend to roll off, put this on, but then you have to re-zero with that on. Okay? So all 3 teams take the mass of your 3 balls. Okay? Now, this team doesn't have one, so as soon as one of the other team finishes, you can measure it back. You can go and some of you measure on this.
I was gonna help somebody measure.
Okay? I'm going to run to my office, to the classroom and get all 3 teams to measure the mass of all 3 balls.
Rubber
Yeah.
ball is 30.
Can I get a laugh, please?
Yeah.
The rubber ball
I
is
ain't got one
30.
either.
Yes.
Okay?
And the round ball is...
Not proud to that's okay.
Can we use the gram scale?
I'm sorry?
Can we use the gram scale?
That's not mine to give, so I wouldn't mind it, but I just hate to use their equipment.
69.
Hey, Mr. Feller, I need a laugh. No.
Okay, I'm bringing.
Okay, what about that target incline plane?
Okay, who else needs a lap?
It's 30.
Who else needs a lap?
0.1, 30, and 69.
Okay, everybody got a lap? Okay, have you measured the mass of your 3 balls in grams?
Yes.
Okay? Everybody got one? All 3 teams got to a scale?
Yes.
Right? All right, now let me set up your, this is what we call, it's okay. an inclined plane. Okay? We're going to set it up at 5 degrees. Okay? Where's your inclined plane?
Right here.
Set it up at 5 degrees. That's the lower one. Yeah, right there. Okay? Set it up at 5 degrees.
What about the second?
Hey, how did y'all do that? Did y'all?
5 degrees.
Using the meter stick, and using the meter stick to determine the length of the track.
So that way,
Okay.
what is that? 38.
Now,
Would that be 38?
everybody start at 5 degrees, and at the lower side of that thing, the longer side is 5. Okay? Now, what you're to do, before you start measuring with the balls, each of the teams has a meter stick. I don't know where they've gone, but each team has a meter stick. You have 2. Okay? So this is great. There's supposed to be 8 people here.
One went out from them.
Okay.
7? I mean,
Okay.
2.
Oh, okay.
No. What was
I
that?
asked if everybody had done them. Okay. Those who have scale, you got it. You can do it. Okay. Take the meter stick. Where's your meter stick? Okay. All right.
This was 38.
Okay. Take your meter stick, and on the centimeter scale, put the 0 into the scale
I'm sorry, my
at
brain's
the
not working.
end point here, and then measure to
Why
that
is it tripping now?
plate, the inside of that plate, to the nearest 1/10 of a centimeter. You're a 1/10 of a centimeter. Did everybody see that? Okay.
That's just so they don't
You're all
fall off.
supposed to be at 5
Okay,
degrees.
That's 39.
Are you at 5 degrees?
That's 39.
Are you at 5 degrees? Okay.
Yeah, about 2 grams.
Okay. You already got it? Okay. Oh, okay, good. Okay, now, on the attached data sheet, okay?
Say 8 for the, that one.
Okay, do the nearest 1/10 of a centimeter. Now, what's your problem? You put the 0 down there,
Like it's moving, it's getting heavier.
okay?
Right, there we go.
Okay, but do the centimeter side, okay?
So,
Okay, the centimeter side. This is the centimeter side, okay?
also 55 grams for this one.
Okay. And then the nearest 1/10 of a centimeter inside of that plate. Okay.
Okay.
We still got one team taking ground measurement. Have you got them all done? Okay. And you got all the meter sticks, the length stuff. Okay. Now, what you do here. You're off.
I put one of them.
Okay, got it?
One day.
Yeah.
Especially if you want to. 4. Okay. Let's go down.
Okay.
How do you?
All right.
Not 30.
Now,
42.9.
second.
Yeah.
Okay. All right. Now, how to operate the stopwatches? Pretty simple. Do not hit the middle key button at all. Your start, and your stop are over here. Sometimes they start and stop, and sometimes they don't. Okay. The reset is on at 10 o'clock. That goes back. Okay. Listen up, folks. This team here, your first digit, 2 of those are not showing. It looks like 7.00. You're not going to use that. That's a 0 out there. You're only measuring the first large number and the 2 small numbers. So you start, stop. That was 1.47 seconds. 1.47. That's what that stands for. Then you reset at 10 o'clock. So don't pay any attention to the 7 in front. It's not a 7, it's a 0. Okay, now listen up. Here's what you can measure. Okay, what I would recommend is turn to the back of one of these pages, like the back of that front page. And then at each height, with each ball, you do 3 time measurements. 3. So they're starting, it seems like with the plastic ball, they will measure. Now, I would suggest the person who releases the ball also holds the clock. And start, stop. You stop when it bumps on the bottom end. Okay? And then you can reset anytime you want to. Okay? There's no rush on that. The rest of you take down. You take 3 measurements, and what I would recommend, listen up, is write the 3 measurements on the back of this page. Now, you could either average the 3, or easier, throw out the high, throw out the low, and take the middle.
All right, cool.
Now, if one of those is really off, way different from the other 2, take another one. So you get 3 that are relatively close, and then throw out the high, throw out the low, record on this side, on the data table, your middle time. That's what you put, not just the only time you measured, the middle time. You take 3 measurements, record the middle one. So if you've already taken 1, or did y'all do 2? 1. Okay. Okay. Take 2 more, and as long as they're relatively close, throw out high and low. Record on here your middle time. For each ball at each elevation, do 3 measurements. I would say write them down over here, and then throw out high and low, as long as they're relatively close, and then record on this side. Make sense? It's easier than averaging. I got it. Okay, Harold, take it. Got it? Okay. If you have any questions, ask. Do not assume, ask. Okay?
1.37.
1.37.
Okay. While y'all are taking your measurements, I've got to go make a copy. I'll be right back.
You got what? 1.4. The time for the
We're just going to stick with 1.35. Let's do 1.35. Fine. You got 1 pass, I'll never see you again in my life.
Y'all have some real hate going on there, for real.
I was about to say, he just said that, next thing you know, they're going to be engaged next year.
How about that?
Oh, wait, you never
Have you already done 2 measurements?
Yeah, we're
1.23.
Okay.
That's his job. Okay.
You got iPhone?
What was that first one?
We're doing the transition to average.
What was the first roll number? 191.
What was it?
Hey, I got ahead of this.
Okay. Please, if you have any questions to ask, don't make any assumptions that are going to get you into trouble later, like happened last time.
Wait, 1.10?
Yeah. I did it again. Same topic. What are we going up?
Right here, this is what we're going to measure for.
We just did 10, right?
The last one for the rubber is 1.9.
Okay, what was the first one?
You just got one?
1.03.
1.00.
Where do the rest of
Yeah, the rest we have everything.
What was the,
182.
Again?
That's all right, sure.
What's up there? What's up there? What's up, Bob? What's up next?
132.
Okay, the question is, how do you calculate? Okay, you filled in times on the second the first blank column, right? The second blank column says average speed. How do you get that?
One more rubber.
What is average speed?
Distance divided by time. Distance divided by time.
Distance divided by time. What's your distance?
40%.
Okay, whatever you measured that distance was, and then your time are the times in the first column.
What decimal place we need around to?
What have we got? About 3 digits?
What,
So I would
how do
do
you
3
do
digits.
that?
Yeah.
Distance times.
Distance divided by time.
Distance divided by time. Is that what speed is?
We had to stop.
Okay, I'm going to pause. All right, we're recording now. Okay, now y'all got an average speed by doing distance over time, right?
Yes.
And that gave you an average speed. Now that you know an average speed, you remember another formula for average speed. V-I, not minus, average. Okay, now for me to average your grades, I take one grade and subtract the other one from it and divide by 2, right?
No.
Well, I better not. What do you do? Add them together and divide by 2. So V final plus V initial plus V final divided by 2. We already know an average speed. You wrote it down in the second column, right? Well, now, let's multiply both sides of the equation by 2, and that wipes out your denominator, which I'm all in favor of. What is your initial velocity?
0.
0. You released it from rest, remember? So guess what your final velocity is? Twice the average velocity. Why is this true? Under what conditions is this formula correct?
So we just multiply average speed by 2.
Yeah, average speed by 2. That's it, exactly. Okay? Why is it true? Because we have uniform acceleration. It's not, the acceleration is constant. So therefore we can have that. And that's twice the average speed. Think of it this way. The initial speed was up here. The final speed was down here. The average speed is right in the middle. Average the two of those together. So the final speed is twice the average speed. All right? Everybody got it?
Yes.
I got to return this. I stole it from the other lab. Okay.
Okay, what you got? You got 20? Oh, you got no rubber.
Was there a question? Okay, I'm going to pause this. If there's no. All right, the question was, how do we get average acceleration? How do we do that? How do you get average acceleration? What's the formula for it? Average acceleration. Anyone remember? Average acceleration.
Is it velocity final minus velocity initial?
Over time.
Okay, change of velocity over change of time. You got your final velocity right? You got your initial velocity right? That's pretty easy to subtract, right?
Alright, what is it?
Delta V.
Okay, average acceleration is change of velocity over change of time. What is your change of velocity? You went from 0 to whatever your final velocity was, right?
We're not doing.
Okay, so what was my velocity?
Oh, you haven't calculated final velocity yet?
It doesn't say velocity.
Say again? Okay. Yeah, average speed and velocity were counting the same thing. Okay? But then your final speed was what? Have you been doing the calculation?
Yes. So you would add, subtract these two.
Wait. Your average speed isn't your initial speed. What's your initial speed?
0.
0! So I can subtract that. Okay.
So 34 seconds. Subtract that.
No. What did we say it was?
El subtracto, el zero.
Okay. Change of velocity over change of time. What's your change of velocity? Yeah. Not average speed. Change of velocity is your final minus initial. Right. Over time. And what is your final speed?
Final speed.
Yeah, that column. And what's your initial speed? 0. The time.
Final velocity.
Divided by final 0. 0 is yeah. The initial velocities are all 0. You release them from rest, right?
Just to make sure my thing is right.
Okay.
It's final minus initial,
Right.
which is basically just final,
Right.
over time, right? So it would be 59.8 divided by 1.
That's it.
Alright, cool.
Let me see your numbers again just to see how they were looking. Okay. Yeah, that's what you read.
What do you got?
All right.
I know.